Well, let's look now at some activation functions. So we have already seen one activation function. This was the step function, but now let's look at other ones. So we could make a linear activation function that has this form here, ax plus b. So this is just a linear function. So, but if you only have linear functions throughout all of your neural network, then basically you can show that having only linear activation function leads to your network being a linear model. And if you have a linear model, then well, then you can only model certain linear problems. And in practice, it has been shown that, or practice has shown that nonlinear models are much more powerful and much more suitable for modeling many real-world problems. Another one is the step function. That's the one we've already seen before. Graphically, this is given by this graph here, where you have 0 if the input argument is less than 0 and 1 otherwise. On when it's exactly 1, it's a little bit unclear which value should be given. The problem with this one is, so this was first, it was the historically first specification. Secondly, it's not differentiable everywhere because there's a point here where it's not differentiable. But that's not such a big problem if just one point is not differentiable. More problematic is that the derivative is actually 0, right? That function, except for this point here where it's not differentiable, the rest of the points, the derivative is all 0. And if we do optimization with derivatives and the derivatives is 0, then the optimization does not work. So that's why people, after the initial perceptron algorithm or the perceptron model has been introduced, they chose a different one. And this was one of the most popular choices, the so-called sigmoid, or also called logistic activation function. It has this mathematical form, 1 over 1 plus x to the minus alpha, where alpha is a parameter. And what you can see here is this function, it takes the value 0 if the input argument is very negative, and it takes the function 1 if the input argument is very positive. So it kind of looks similar to the threshold function, but a little bit different also. And it could be considered an approximation of the step function. And depending on how you set this parameter alpha here, not alpha, but a, so depending on how you set this parameter a here, the function looks differently. We can look at different graphs. If you put a to 0.5, it is flatter. If you put it to 10, it becomes steeper. And now with 10, it really looks like the step function, right? So the disadvantages are, so the advantages of this specification is that it's a differentiable approximation of the step function. So we can actually do optimization with that, and we can plug it into modern optimization algorithms. But it kills the gradient. So what does that mean? So the derivatives, if you take the derivatives up here in the positive and the negative region, you know the derivative is well, you look at the change of the function if you change the arguments to the function, and here you see it's very flat, so the gradient become very close to 0. So there it's not good in this region. Outside a small area around the value 0, the gradients become 0, and then optimization becomes difficult. And it's also not zero-centered. Zero-centered means the value of the activation function is not zero-centered. You see it's actually centered around 0.5. So it goes from 0 to 1, and the center is 0.5, so to speak. So, and if empirically it has been shown, um, if the value of such activation functions are not centered around 0, but they have some bias, so to speak, um, some positive or negative value that is their center, then these activation functions are harder to optimize, and the networks that use these activation functions converge slower to good solutions, right? So zero-centeredness is a property that we typically like. Okay, and yeah, there's a mathematical explanation why zero-centeredness is a good thing that you want, but we'll not go into that at this point in time. Then instead of as a replacement for the sigmoid function, the tanh functions, uh, tangents hyperbolicus has been introduced, and this looks actually very close to the sigmoid function. It has the same form. It goes from -1 to +1, and therefore you see it's actually zero-centered, right? So it has zero-centered outputs, but it still kills the gradients in a certain region. So here the derivative is almost zero. Here the derivative is almost zero, or is close to zero as well. Then, uh, well, first sigmoid has been used for decades. Then after tanh, I think starting in the 1990s, tanh became popular and replaced sigmoid because it had the zero-centered property. And then only in the like 2010s or 2010, people introduced another activation function, so-called ReLU, rectifier linear unit. And this has also a very simple shape, or has a much simpler shape also. It's just a maximum of 0 and x. So in the positive region, it's actually just the identity function. And in the negative region, it's 0. So yeah, this was proposed around 2010 as an activation function, and it has many pluses. So the gradients don't die in the positive region. So we don't have this property that the derivative becomes 0. So you see the derivative here is 1 because the derivative of x is 1. So you don't have gradients or derivatives that become 0. So this is very good. It's also computationally efficient. You don't have to do exponentiation or something, which you have to do for the sigmoid function. So that's cool. And experimentally has been shown that if you use that, okay, then your network converges faster to a good solution, right? But negatives are it's not zero centered, right? Because it goes from 0 to infinity, and it's certainly not zero centered, and it kills gradients in the negative region, right? Because here the derivative is 0, so it's not good here. Therefore, people have introduced improvements upon that, like in 2013 to 15, for example, the leaky ReLU, where you have in a negative region you also have a linear form, but it's like adjusted a little bit so that the slope is not as steep. And this has the good thing where the gradients don't die in the positive region, it's computationally efficient, and the gradients also don't die in the negative region, right? But it's still not zero-centered. Then people have introduced parametric ReLU, where you instead, like here they just use this leaky ReLU function, where they added 0.01x in the negative region, but you can actually make this a parameter alpha, and then this becomes part of the network to optimize, and then maybe the network can decide what does it favor. Does it want to become a standard ReLU or leaky ReLU or something else? And then there's the max out activation function that has been introduced by Goodfellow in 2013. So that generalizes ReLU and leaky ReLU. And how does it look like? Actually, it's a little bit different. Instead of having only one set of parameters W that is multiplied by the input X, and it has instead of that it has two sets of parameters, W1 and W2, and it takes the maximum of these. So now it can learn to set W1 to 0, for example, then it just becomes the maximum of this argument and of 0 and the other argument. So this becomes then a standard ReLU function. Or it can set the W1 to other values, and it can become a leaky ReLU. It can generalize many other things. So that's actually a cool thing, but it's computationally expensive because now for each um, for each unit you have two weight vectors, and that means for each layer you have two weight matrices. And actually, people mostly don't use that in practice nowadays. Empirically, as I have said, it has been shown that 10H is better than sigmoid. Currently, the ReLU was the most popular activation function as of 2015. However, times are changing quickly, and with more modern architectures such as BERT, still other activation functions may be in use and may be popular at the moment. I would like recommend to you to try out different ones and see whether they improve your results, such as leaky ReLU, max out, or ELU, which is another generalization of the ReLU function, like a differentiable generalization. And don't use the sigmoid function in practice, maybe in home exercises, but in practice, if you want to solve a problem, don't use sigmoid or don't use the step function. Well, the step function would be the worst of all. And activation functions are a hyperparameter that you should try out. I mean, you should try out different ones. Good. So now let's talk about the derivatives. Yeah, what I want to say. Well, we have this activation function. It's a linear one. This is a identity function. The logistic, that's a sigmoid, that's a 10H function. We can look at the derivatives. What you see here, if we plot the derivatives, then the linear has a good derivative. It's always 1. So why is that good? Because the gradients don't die. Optimization can work. But the problem with the linear function is that you get a linear model out. So a linear model is not so powerful. And here you see the difference between logistic and 10H. And what you can see here is logistic, that's the sigmoid function. It has much lower gradients compared to the 10H. That's what makes 10H empirically better.